Hello, my name is Jason Iwachow, and I'm a technologist for Environment Canada with Alexei team. I will be presenting on the updates to our aircraft probe calibration capabilities since the Icicle campaign. I will quickly summarize the starting point of the state of calibrations at the end of last Icicle campaign in 2019. Calibrations generally include checking optical alignment, laser light mapping, and recording calibrated targets. In this presentation, I will restrict myself to the subject of recording of targets. For imaging probes, we have a spinning disc mounted on a computer-controlled XY stage. A glass disc with mono-sized, monospaced targets is moved in the, ideally, entire sample volume of the imaging probe, X, Y, and Z. A set of 26 different sizes of dots, 8 discs, is recorded on each probe. The speed of the motor was limited because a flat motor was chosen for geometry considerations. This limited the tangential speed of the targets to about 12 meters per second for the entire set of discs. For scattering probes, we were limited to throwing NIST-traceable glass beads or polystyrene beads through the sample area. This method doesn't allow positioning in the sample area. The response of the instrument to beads is different than water since the index of refraction is different, requiring a correction factor to be applied to the results. Lastly, the size of the beads are not uniform. They are Gaussian distribution around the central peak size. If the bins are not properly selected to minimize the effects of the non-monotonic Mie curve, this method won't help you fix the multiple peaks that become apparent in the results. We have all been facing new challenges as our work situations have been evolving due to COVID. The bad news is that all ECCC employees, including non-critical technologists such as myself, were sent home in March 2020 and have not returned since. I also had some parental leave. The good news is that I have space for our home office and lab in which to continue working. Private equipment such as 3D printer, oscilloscope, and waveform generator is supplemented with ECC test equipment for calibration development. Condensing down from our ECC 2,500 square foot lab into a 150 square foot room has its limitations, the biggest one being I don't have any probes, and the second biggest being airborne dust for optics work. Nevertheless, there has been some progress. So what's new since Icicle? A droplet generator is being developed, a new set of glass discs has arrived, and a high-speed motor update is being developed. One way to get around the problems of spinning discs and glass beads is to produce water droplets of known size. We are developing a droplet generator based on the design from Spec Inc. The basic setup is described in Sarah Lance's paper in JTech. The droplet generation components were purchased from Microfab Incorporated. The idea is that a piezoelectric crystal pipe, called the injector, is mounted vertically and filled with water. As a voltage waveform pulse excites the piezoelectric material, it shrinks and expands, causing droplets to be forced out of the orifice at the bottom. In operation, a slight negative meniscus on the orifice works best. This water pressure is maintained by placing the water reservoir at a slightly higher elevation than the orifice. One more bit of theory. When a collimated light source, such as a laser, is shown at a transparent spherical object, on an angle shown here, there is a refracted and reflected light from the droplet. The space between the light is directly related to the size of the droplet. The diagrams are taken from Wendish's paper. If the droplet is moving, a long exposure on the camera will cause two parallel lines of light to be seen. The measurement of this glare is a precise way of inspecting the droplets for size. Microfab's jet drive control box allows the user to control the voltage waveform to the injector and strobe output with a specified delay. Since the droplets are highly repeatable, a strobed light can visibly hold still crisp images of the droplets so that inspection of the droplets at any stage of the ejection can be done using a low-speed microscope camera. I have been able to produce a basic setup with a 30 micrometer orifice injector, Jet Drive 5 controller, Infinity X 32 megapixel camera with adjustable zoom microscope, strobed LED for droplet inspection, and diode laser for droplet sizing. The laser sits in a track which fixes its angle to the optimal angle for calculating the glare distance. The LED also sits in the track, and the track is attached to the camera. The camera is mounted on the lab jack and a manual X-axis translation stage. Many of the parts are 3D printed using PETG plastic. Many people hold grudges against using plastic parts, but PETG has proven, at least to me, to be quite rigid and adequate for most of the parts on this scale that aren't the primary structural parts. I recommend investing into a Prusa MK3S. It will save you a lot of money on machine shop bills. Here is a test of the injector. Notice the thin drops being thrown about 10 centimeters below the injector. Here is a video from the camera setup with only the strobe LED on, no laser. 33 still images were generated using increasing strobe delay and were assembled into one clip. With the particular waveform, it was generating 3 drops per pulse. Here is a picture of the full setup, LED strobe on and laser on. Notice that the glare is measurable. Also notice that the droplet is traveling diagonally. This is because the injector face has been wetted and is difficult to clean or dry off due to its tiny size. A precision reticule can be used to determine the particular zoom setting. In this case, we see that the reticule is about 876 pixels for half a millimeter, while the droplet glare distance is 63 pixels. This means the glare size is 36 micrometers, and therefore the droplet size is 33.2 micrometers. My pictures have been sort of a mix and match, and that's because the setup is constantly being revised, and I haven't been keeping a detailed video record of the changes. I have been playing around with a few different setups for flow tubes to speed up the droplets and control their position a bit better. The groundwork for the programming bit of this project, including the control/interface with the linear stages and picture capture, has already been accomplished, as will be seen by the high-speed motor upgrade. In order to properly test the older PMS probes for electronics response, calibration targets need to be taken up to a speed which starts approaching flight speeds. As previously seen, our spinning disc calibration system is speed limited due to the motor chosen. A suitable replacement has been purchased. Unfortunately, this also required a replacement of the motor controller. This new controller can handle high speed but is analog controlled. The new motor is a 2-pole brushless DC motor with Hall sensors. The new motor is long and thin, whereas the old motor was fat and flat. However, exactly how this will affect the sampling volume will be seen when we return to work. Originally, the flat motor was chosen to fit between the probe arms, but it is possible that a narrow motor will allow for enough shoulder on the disc so that the targets will remain visible to the probe without the motor having to enter between the probe arms. The test setup involves the motor controller with analog voltage control. This is controlled by an Atmel 328P microprocessor, also known as a Arduino Nano V3, a simple circuit to convert the PWM output of the microprocessor to an analog DC voltage is shown in the schematic here. It goes through a low-frequency filter and DC buffer. Finally, the computer can control the microprocessor, webcam, and linear stages. The linear stages and microprocessor are controlled through serial ports. The webcam is captured using DirectX's Direct Show. This controller program is made in C# using Visual Studio 2019. The first test without any torque load shows the motor can achieve a top speed of approaching 60,000 RPM. The reality is that when a glass disc is attached, the top speed will be reduced by the amount of air resistance torque. I 3D printed a glass disc analog since I don't have the axle attachments at home for the actual glass disc. As you can see, the heat stresses from 3D printing on the thin plastic piece cause it to warp slightly. This unbalanced load might be dangerous to run up to speed. Let's try anyways. Success! Top speed is almost 400 Hz, 24,000 RPM. At a radial distance of 23 millimeters, the tangential speed is 57 meters per second. With a smooth surface, the glass disc should go faster. The new glass discs are for the spinning disc calibrations. Unfortunately, they arrived at the ECCC building, so I couldn't get any pictures. Basically, they are a set of glass discs with only one mono-sized target per disc. This is a necessary upgrade since the new probes like HVPS and 2DS Gray have a wider sample volume, which would cause two sizes to be visible simultaneously with the old discs. I hope you enjoyed my presentation. Thank you for listening.